Okay, we're working in section 4.1. We're talking about inverse functions. Let's look back at these goals we have for the section and see how we're doing so far. So the first goal was to identify whether a function is one-to-one, and we've done that, and we're going to practice in just a minute with example number 3. The second goal is to check whether two functions are inverses of each other, and we haven't done that yet. That's coming up though in this video. That's example 5. And then the third goal is to find an inverse from a table, a formula, or a graph. And we've done all that, and we're going to practice some more with a formula. The formulas will be in the next video. And the graph we're going to practice in just a minute in example 4. So we can see where we're going. Okay, so example 3, is each graph invertible? Remember, to be invertible, the graph just has to be one-to-one, or it has to pass the horizontal line test. And so if we imagine horizontal lines across this first graph, you see that everywhere we draw a horizontal line, it only hits the graph one time. So the answer is yes. This function is invertible. Yes, this function is invertible. It's one-to-one. And you could say one more thing. You could say it passes the horizontal line test. The next graph looks like a rational function that we studied in section 3.5, and so does it pass the horizontal line test? Think about it. The answer is yes. It does pass the horizontal line test. It is one-to-one. It is invertible. It might seem like a horizontal line here near the horizontal asymptote might hit more than once, or it might look like this curve right here is a horizontal line, but it's not. Remember, it's always getting closer and closer to the horizontal asymptote, and so it's always rising just a little bit more, and so a horizontal line only hits one time. Okay, and then in this last example, we have a function that is not invertible and not one-to-one, and does not pass the horizontal line test. This horizontal line hits the graph 3 different times. This graph looks like a polynomial, looks like the graph of a polynomial function that we studied in section 3.4. Okay, let's go on to the next thing. Let's in example 4, we want to use the graph to sketch the graph of its inverse. And so this graph should look familiar. This is the graph from part A in example 3. And do you remember how we did this? We talked about doing this problem in a previous video. What we said is that the graph of the inverse is a reflection over the line y equals x. And so what we need to do first is we need to draw the line y equals x right on the coordinate plane. And then in order to and then we need to reflect h of x over y equals x. And so there are a couple little tricks to do this correctly, to do this successfully. The first one is to remember that a point on y equals x is going to remain stationary. And then the other trick would be to remember that the x and y coordinates switch position. So this x-intercept looks real good. This x-intercept is going to become a y-intercept, and it should be over about right here. And so with that, we should be able to connect up the curve so that it looks like a reflection. So we should have something like that and something like that. The sketch is not perfect, but I think it's good enough to get the idea. And so again, you might want to turn the paper or 45 degrees, or you might want to turn your head 45 degrees to convince yourself that that really does look like a reflection. Okay, in example 5, let f of x equal x cubed minus 1 and g of x equal the cube root of x plus 1. We want to use the definition of an inverse function to determine if g is the inverse of f. And so this is a problem we haven't done before. Notice the directions are real specific. Use the definition of an inverse function to determine if g is the inverse. So you know how to find the inverse of a function like f of x or g of x, and in theory you could go through that process to see what the inverse is, but that's not what the problem is asking. The problem is asking to use the definition, so we have to know that definition. That definition says we need to check these two compositions, and we need to see what they come out to be. So that's what we're going to do. We're going to check f circle g of x, and when we're done with that, then we'll check g circle f of x. So f circle g is the same as f of g of x, which is the same as f of, now g is the cube root of x plus 1. So that's going to get plugged into the f function, which says take the input and cube it, and then subtract 1. Okay, so we've created the composition. Now we just need to simplify it to see what we get. And so first thing you should notice is that the cube root and the cube are going to cancel, and we'll be left with x plus 1 and then a minus 1 at the end, and then sure enough that's equal to x, which is what it's supposed to be equal to. And so so that worked, and so it's certainly looking good that the other one will work as well, but again we need to write it out. So let's go ahead and check the other composition, g circle f of x, and we'd have g of f of x, which would be g of, and then f of x is x cubed minus 1, and so we can plug that into the g function. The g function says take the input and add 1, and then take the cube root of all of that. And so this time the minus 1 and the plus 1 cancel, and we're left with the cube root of x cubed, and those cancel, and we're left with x. And so the conclusion is yes, f and g are inverses. And we're done.